All right. Recall the definition of a surface from Calculus 3, right? So in Calculus 3, we worked with surfaces in the 3D space. Right? So, and a surface in Calculus was given by parametric equations. So here is an example. So something like this. So, we probably, so x should be some equation in, say, u and v. So something like cosine u, cosine v. Y is going to be probably cosine u, sine v, and z is, let's say, sine u. Something like this. So the input, so it is a function from a two-dimensional space to the three-dimensional space. The input has two variables, u and v. The output has three variables, x, y, and z. So, and our surface is just the image of such a function. So in order to verify that this is like a good smooth surface, we need to check that, so we need to take the vectors Ru, which is really nothing else but the vector of partial derivatives, dx, du, dy, du, and dz, du. Well, and the similar vector are Rv, so the dx dv, dy dv, and dz dv. And we would need to check that these two vectors Ru and Rv are linearly independent. Now, but then let us think a little bit about this. So what does this all mean? So where do these u and v live, right? So we can think of u and v as a point in some special two-dimensional space, say u with coordinates u and v, and we can kind of just restrict, well, for the sake of the story, we're going to restrict it. So, I mean, when you work with surfaces in practice, then very often you let u and v to be like all possible points on the plane. But for the sake of this definition, it's more convenient to restrict it to some open disk, right? So u and v, they live in some open disk on the space on the plane uv, right? But then our surface as a whole can be thought of as a function from the space, from this open disk to our, well, basically to our three-dimensional space. And well, this is our surface probably in our three-dimensional space. So f is a function from this open disk to our the actual surface, right? So, and the image of this function is probably some little open disk here. So, which is why in topology, what we do, so the main property that defining property of a surface is that if we have our surface, then every point on the surface should have some small neighborhood that is homeomorphic to an open disk. So it looks precisely like an open disk. Right, so this is my u of x. So if this is x, and this is my little neighborhood that is homeomorphic to an open disk. Now, what kind of surfaces are we going to have? So this is, by the way, it is a closed surface. So notice that there is no place here for the boundary of a surface. So a cylinder would not satisfy this because or an annulus, because if we have an annulus, so then a point here, its a little neighborhood is homeomorphic to half a disk rather than a whole disk, and so it's not a surface from this point of view. So later we will see that something like a cylinder is a surface with boundary, which is a very similar object. But now let's just work with closed surfaces, so surfaces without boundary. So a sphere is a surface. So a torus is a surface. Well, something like a torus but with two holes is a surface, and so on and so forth. Now, a compact surface should be covered by finitely many such coordinate neighborhoods, right? So if we, let's say, look at a torus with well, like a double torus with two handles or two holes. So so every point here has a boundary that is homeomorphic to an open disk, and you can imagine that if it takes sufficiently many of these these disks, we will cover the whole torus. But it's not always the case. So here is an example. So imagine like an infinite strip, infinite like a maybe something like a cylinder, and we make holes like those in a torus, and we make infinitely many of them on both sides. This is clearly a surface, but it's not compact because, I mean, it's just extend infinitely in both directions. So we will not be able to cover it by finitely many coordinate neighborhoods.